In our documentation, we explain the relationship of memory to cores, or referred to as CPUs. So here it is in our documentation. You'll find it under docs.hpc.arizona.edu. And then on the left side, go to the user guide, then down to running jobs with SLURM, and then you'll find total job memory versus CPU count. But sometimes it's easier to see it in relationship to an actual physical node. So let's go take a look at one of those. So here's an example of a compute node. This is out of Elgato. So it's older, but the geometry really hasn't changed inside a compute node. So what you see here is this is either referred to as a socket or a processor, and there are two of them. We have two in each of all of the compute nodes because that's the most price performant option. And within each socket or processor, there are cores. What's confusing is that SLURM will refer to these as CPUs, as a core. But generally in hardware terms, the CPU is the physical device. So let's just say these are CPUs and inside them have cores. This one has only 6 cores in here and 6 cores in here. But Puma has 48 cores in here and 48 cores in here. And I'm touching it because this one's dead. I wouldn't normally touch a live machine because static discharge. You'll also see DIMMs in the DIMM slots. And in Puma, they're all occupied. Puma has 32 gigabyte DIMMs, and there are 16 of them. So if the math is right, that's 512 gigabytes. And here is a disk. All of our compute nodes have a disk. The new ones are NVMe, so they're faster. And so that's mounted as temp/TMP. So it's very efficient, quick storage for your compute jobs, but it's transient data. When your job ends, the space gets cleared out. But if you...
How big are those SSDs you mentioned?
The ones in Puma, they're 2 terabytes, but take out the operating system and you're left with about 1.3 terabytes of usable space and /temp. What is useful in this configuration to see is what's contained within one node. So if we go back to Puma again, and there are 48 cores and 48, so that's 96. 2 of them are kept reserved for the operating system to use, so we're down to 94. If you run a job that's any number divisible or close to divisible into 94, you are efficiently using the space. So 48 is pretty close, that's good. 24, 12, 6, 4, 2, 1, something like that. Your job will run on this node, and if you're running, let's say, 4 core jobs and you need 10 of them, you're using 40 cores, and chances are it'll run on one of these and fits into one space. For memory usage, Puma has works out to 5 gigabytes per core. So it's the 512 gigabytes divided by the 94 cores, comes to roughly 5. So if you need 10 gigabytes, you're going to get 2 cores. If you need 20 gigabytes, you'll get 4 cores. So there's a strict physical relationship between the core count and the memory capacity. All right, now that we have seen the actual physical node, let's see how it looks to SLURM. In this example here, this is a really simple one. We have defined our job as needing 5 tasks. So the 5 tasks, that'll work out to 5 CPUs. In the next line, we have CPUs per task of 1. Well, by default, a task is a CPU, so we don't need to specify CPUs per task if we're using the default of 1. So let's go ahead and just comment that out. We have nodes equals 1. We want our 5 tasks to all run on one physical node. If we don't put nodes equals 1, it might be scattered across 5 different nodes, which would be really, really inefficient. So we're going to leave that in there. Then the next category we have here in the next variable is memory per CPU, and that's set to 5 gigabytes. Well, 5 is the default in Puma. So there's no point putting that if we're just going to use the default of 5. So let's comment that out. And then we're asking for 25 gigabytes of memory. Well, we asked for 5 tasks. and we set 1 CPU per task, and we're using the default of 5, so 5 5s are 25. So we're going to get 25 gigabytes by default, so we don't need that either. So really all we need to do in the simplest case is specify how many cores we want to use, and the amount of memory will follow as a direct mathematical relationship. So in easiest terms, that's how SLURM addresses and relates cores to memory.